Now, in that definition, we started saying something. We said that when a chemical reaction starts, please pay attention and listen. Hey, look up, look up, look up, look up, look up. Now we said when a chemical reaction starts, that at this point, the concentration of the reactant is very high. Guys, are you with me? Eh? Did you get? When a chemical reaction starts, at that point, the concentration of the reactant is very high. Because I am still here, it's not true. Now, the moment I'm going from here, now if the concentration of the reactant is high, that means the product is beginning 0. Class, are you with me? Now, the moment I am moving, if I start going, remember I'm going to the product now here. If I start going to the product, it means that my concentration will start reducing. Why? This one will start getting increasing. I see it now. So here, this one is 0. This one is what now? Sorry, this one is 100. The concentration is how many? It's not one here. Why this one is how many now? 0. As this one is approaching here, this one will be coming here. It's not true? That's right with me. The concentration of this one will now be increasing. So if I'm moving from here, it is high. The moment I start reacting and I'm going to the product, my concentration will start decreasing. While this one that was 0 will start gaining, will start increasing. Okay. Now a point will now come when the reactant will not become 0. Why this one will not become getting maximum? And of course, at that point now, I've already started going to get it to the reactant. Now, when I go to the reactant again, I will not become 0. Why this one become getting 100 again? Okay, and that is because we say it is again reversible. This coming here, and A coming to B, and B coming to getting B coming to A. Do you understand it? So that's what we mean. Now, when the reactant is just like this marker, now look up here. If I draw this marker up, you notice that this marker was able to come down, right? Now, at that point, it reached a point where this object has to stop on space. It's not true. It has to stop on air before it started getting coming down. Now, it stopped. Why? Yes, it was on motion. Class, are you with me? The marker stopped, but it was also in motion when it stopped. So that's why you call it this type of equilibrium. Sorry, this type of equilibrium we call it dynamic what now equilibrium. Because even though it stops, but it was actually in what now? In motion. Are you with me? Okay. Alright, let's go. Chemical equilibrium. And a chemical system is in equilibrium. For law to say that a chemical system is what? Is in equilibrium, it means that the color of the system, sorry, of the reactant or the species in the reaction is not expected to what now? To change. Now what do I mean? If I started as white, if the color of this body, sorry, of this species, I'm using my body as an example. I'm a species trying to undergo a chemical reaction. If I am white, and when I finish undergoing this reaction, on coming here and I change this to black, I'm not black now in color. Now, if I come back to where I started this journey, I'm expected to what now? To be white. If I'm not white, it means that this is not a chemical equilibrium. It's not a chemical equilibrium. Do you get it now? Because we said that we start using now the rays. Now what does it mean? If it will take me 10 minutes to complete this reaction, and I will use 10 minutes again to come back again to the product, sorry, to the reactant. Now the same 10 minutes should be the same. That's why I said with equal time. So the rate is talking of the time. So the time it will take me to go from reactant to product should be the time is going to take off from product to get it to the reactant. Without no observable change. So that means I'm touching the color. When I change the color of the species, I'm not going to encounter any difference. So if I am white here and I'm coming here and black, it's okay. But if I'm coming from black now, that is product end to this other side, I'm meant to change to get it to white. If I remain black here, it means it is not a chemical equilibrium. The density is also expected to be this, and even the concentration. I see it now. So what is that the thing is just going and coming. But the color, the density, the concentration, all of them are expected to be what now? To be the same. Are you with me? Do you understand what I mean? Okay. Then we are going to take a question. Now these are the phases. Now if the species, look at this one is a species, this is nitrogen gas. This is hydrogen gas. Now when it reacts in the ratio of 1:3, we are going to have an ammonia formed in the ratio of how many now? 2 moles. 2 moles. Okay. Now in this case now, this is nitrogen gas, this is hydrogen gas, and this is ammonia, right? Now all of them are in gas. So that means the name of this reaction is going to be undergoing is homogeneous of here. You know why it is homogeneous? Because all these species are in the same phase of here, in the same state, phase of state. gas. But if I have something like CaCO3, calcium also carbonate 4. Idea, remember that you have to put your arrow there. Remember I told you you must put your arrow to indicate it is a what now? It's a chemical equilibrium, right? Okay, if I have this man going this way, look at that. We are going to have calcium oxide. Idea, which is a quick line. Then I will have CO what now? So this one is solid, calcium, this one is solid. We are using for cement. That's sometimes for cement, limestone. Cement, then this one is what now? Gas. So this is solid gas. Are they the same?
No.
Are they the same phase?
No.
So because they are not in the same phase, this one is what now?
Heterogeneous.
This one is heterogeneous. Right here?
Yeah.
So this is what now? Heterogeneous. So yeah, copy. If I have A plus B, then giving me C plus D. Look at this man. Now this is a chemical equilibrium because if I put this arrow, it means it is a what now? A reversible process, right? It's because a reversible what?
Reaction.
A reversible reaction. Idea. Now, what is the rate? Please look up and listen. We say, if I want to find the rate of the forward reaction, that is R1. Idea. What is it going to be? Look at what I will do. Now, this is the coefficient. Look at the concentration of species A, species B, species C, and species what now? All of this, M is coefficient of A, N is coefficient of what now? B, P is coefficient of what?
C.
And Q is coefficient of what now?
E.
So this one is going to be R1 varies as concentration of A, all raised to the power, idea. Then plus changes to again,
Times.
plus changes to what?
Times.
Then I will have it to the concentration of B, all raised to the power again.
N.
Are you with me? Then R1, of course, you know in variation, once you remove your variation sign, I'm going to remove it and put a cost of here. Yes. If I put a cost, I'm going to introduce a constant again.
1.
A constant value of here. Class, are you with me here?
Yes.
I introduce what?
A constant.
Okay, so here will not be A of M multiplied by B of what now? N. Again, I will call it equation again.
Equation
Wow.
1.
I'll call it equation what?
1.
Okay, let's do for B. Arrow of 2 for the second, for this forward reaction now is going to now C, is going to be S, is going to be C, power what now?
T.
The concentration of this man raised to its power P, then times plus changes to what now?
Times.
Then this is D, raised to what now? Q. Okay? Then if I remove this man, I will put your cost right?
Yes.
I will introduce a constant again.
2.
Then this is C of P multiplied by